Hello. In this video, we're going to look at how we can convert quadratic equations from general form into vertex form. I'm going to show you how we can do it if the quadratic is factorable. I'm also going to show you what we can do if the quadratic is not factorable using a couple of different techniques. So first off, we have a factorable quadratic. If the quadratic is factorable, we can make use of the x-intercepts and symmetry in order to find the vertex and convert to vertex form. So supposing we have this quadratic here, which factors to y equals x plus 6, x minus 1. So from what I know of the graphs of quadratic functions, I now know that this has to go through negative 6, 0, and 1, 0. I also know that it opens upwards because the leading coefficient is just 1. So it's a positive leading coefficient. And I actually also know that the y-intercept is negative 6. Right here, y-intercept is negative 6. That doesn't really end up mattering to this. What really matters is those x-intercepts because the vertex has to be on this axis of symmetry, which has to be exactly halfway between the two x-intercepts. So I can find this axis of symmetry by averaging the x-intercepts. So negative 6 plus 1 divided by 2, which is negative 5 over 2 or negative 2.5. I'm going to keep it in fraction form. That gives me the x value of the vertex. To find the y value of the vertex, I substitute that in to my original equation, or into the factored equation. It really doesn't make much of a difference. But what matters here is I'm going to actually figure out the y value of this vertex. So that's 25 over 4 minus 25 over 2 minus 6, which just a quick calculation on my calculator. So 25 over 4 minus 25 over 2 minus 6 as a fraction is negative 49 over 4. So now I know that the vertex, the coordinates of this vertex, are negative 5 over 2, negative 49 over 4. I make use of that information, and knowing that the a value, the leading coefficient, is 1, I can now write this in vertex form. The vertex form is y equals a, which is just 1, so I don't have to deal with it, x plus 5 over 2 squared, and then minus 49 over 4. So if I can find the factors, I can find the x-intercepts. If I can find the x-intercepts, I can find the average, which is where the axis of symmetry is, and then I can find the vertex to write this in vertex form. Now I am going to come back in a couple of minutes and redo this same equation, converting it using a technique called completing the square. But first I'm going to show you a couple more examples using this concept of symmetry. So we've used symmetry with the x-intercepts, but even when I can't factor it, or even in cases where the quadratic does not have x-intercepts, I can still use symmetry to find where the vertex goes. So let's look at an example here that is not factorable. But what I do know about this function, I can sort of use to get started. So I know, for example, that the y-intercept is at 11. I also know that this opens downward. Now, that could end up looking like this. It could end up looking like this. I don't really know yet. But what I do know is from that y-intercept, there has to be another point that meets up at the same level. So another point where the y value is 11. That's the key here. So I am going to find those 2 points. What are the two x values where y equals 11? Looking for the y-intercept. And the reason I do that is it makes the equation very easy to solve. So I'm solving where is negative 2x squared plus 8x plus 11 equal to 11. The reason this becomes so easy to solve is that the 11s drop away. So now I'm just solving the equation, where is negative 2x squared plus 8x equal to 0, which is factorable because there's at least going to be a common factor of x every single time. In this case, there's a common factor of negative 2x times x minus 4 equals 0. So this means that those two x values, so I have the point 0, 11. I already knew I had that point. That's the y-intercept, no shock there. But I also have the point 4, 11. So the axis of symmetry, so that means it looks more like this second one that I drew. So this is the point 4, 11. But the axis of symmetry has to be halfway between them. I didn't find the x-intercepts. It didn't matter. I didn't have to find the x-intercepts. I just had to find 2 points that were at the same vertical level. The axis of symmetry has to be the average of 0 and 4. Well, the value that's halfway between 0 and 4 is 2. So the x value of the vertex is 2, and I can find the y value by plugging that x value back into my original equation. So I do -2 times 4 plus 8 times 2 plus 11, and I get y equals 19. This means that the vertex is the point 2, 19. And now I know my equation in vertex form. The a value is -2, so y equals -2. X minus 2 for the vertex, and then plus 19. That is the equation in standard form. I'm going to do one more like that, and then I'm going to show you completing the square. Okay, so this one looks a little uglier to start. It's not that bad. I know, for example, that a has to equal 1/3, so already we're off to a good start. I know that this opens upwards. I know that it has a y-intercept at -4. So it either is going to look like this, or maybe like this, but either way, I know that I have some other point where y equals -4. So I'm going to solve this equation. When does 1/3 x squared plus 2x minus 4 equal -4? As before, and the reason I like using the y-intercept is because now these are going to cancel out, and I end up with a very simple equation to solve. 1/3 x squared plus 2x equals 0. You can choose to multiply through by 3 if you don't want to deal with factoring out fractions. It's not a terrible idea because people do make a mistake when they factor out the fraction here. I'm going to factor out 1/3 x, leaving me with x plus 6. Remember that when you divide, 2 divided by 1/3 is the same as 2 times 3, which means that these are happening, these 2 points would be 0, -4, no shock, I already knew that one was there, and -6, -4. So we're dealing with this point right here. It's not this one, it's this one. But most importantly, the axis of symmetry. That's what I really care about. The axis of symmetry has to be exactly halfway between 0, -4, and -6, -4, which means x equals -3. I take that -3, I plug it into my original equation. So 1/3 x squared plus 2x minus 4, and I end up with y equals -7. So that means this vertex right here is -3, -7. And now I have all the information I need to write my equation in vertex form. Y equals 1/3, that's the a value, x plus 3 for the x value of the vertex, and then -7 for the y value of the vertex. So we've used symmetry in all 3 of these cases to write my equation in standard or vertex form. All right, I said we'd go back to that first equation and do something called completing the square. So that is what we're going to do. So just moving off to the side here, the equation that we're dealing with, the function is y equals x squared plus 5x minus 6. Completing the square basically says, let's ignore the -6 for a moment. What would it take to have a perfect square trinomial, so plus something, and I'll just keep the -6 off to the side, so that this bit right here is a perfect square? Well, remember that perfect square trinomials are those that are in the form, let's say, x plus a squared. When I distribute it, is x squared plus 2a plus a squared, 2ax, sorry. So whatever the coefficient of the x is, half of that squared is the constant term. So what I'm going to do, so in other words, I'm saying 5 is 2a. So 2a equals 5, which means a equals 5 over 2. This means that a squared is 25 over 4. So what it's going to take to make this a perfect square is not to minus 6, it's to add 25 over 4. But I can't just add 25 over 4. That changes the function. So I have to subtract 25 over 4 to keep it balanced. What this now means is that the x squared plus 5x plus 25 over 4 is a perfect square. So I can factor it. Y equals x plus 5 over 2 squared. What's left over is minus 25 over 4 minus 6, which is minus 24 over 4. And if I combine these together, I get negative 49 over 4, which is exactly what I got the first time. X plus 5 over 2 all squared minus 49 over 4. Same process. All right, we're going to do both other examples the same way. So I've got the function y equals negative 2x squared plus 8x plus 11. I don't have a perfect square. Notice that in Vertex form, I never have a coefficient in with the x. So I'm actually going to factor that coefficient out, but I don't need to worry about the 11. I'm just going to kind of leave the 11 off to the side for a moment. So I have y equals negative 2 x squared minus 4x, leaving myself some space, and I've just got the plus 11 over here. I could factor the negative 2 out there, but that's going to introduce fractions. I don't have to deal with it. So now I have to figure out what do I have to add and then subtract to keep it balanced that would make this a perfect square. So I need to add something and I need to subtract something. Well, remembering the form, the coefficient of x has to be 2a. So 2a equals negative 4, which means a equals negative 2, which means a squared equals 4. So what I need to be adding on is 4, and what I need to therefore be subtracting to keep it balanced is 4. The part highlighted in yellow now is a perfect square trinomial. So what I now have is y equals negative 2 times x minus 2 all squared. All right, so here's where it gets a lot of people forget to do this part. That minus 4 was in the brackets as well. I need to subtract it in the same place that I add it. So I need to distribute that. So this becomes plus 8 and then plus the 11 that was already there, which gives me y equals negative 2 times x minus 2 all squared plus 19. That is the vertex form. It does match exactly what I found the last time. Minus 2 times x minus 2 all squared plus 19. So completing the square is an alternate way. You can find a vertex using symmetry, or you can find it using completing the square. In some cases, they're kind of equivalently difficult. In this next example, there is almost no reason you would want to, well, this one's not too bad as completing the square, but it's really easy by symmetry. So our equation, our function, y equals 1/3 x squared plus 2x minus 4. All right, so my first stage is to factor out the 1/3. So be really careful when you're doing that you remember that dividing out 1/3 is the same as multiplying by 3. So I have x squared plus 6x. I'm leaving a bunch of space, and minus 4. So I need to add something and then subtract it so that I don't actually change the value here. And what that is, well, 2a equals 6, so a equals 3, which means a squared equals 9. So I need to add and subtract 9 to get a perfect square trinomial. The part in yellow is a perfect square. So what we now have is y equals 1/3. X plus 3 is what that is. So x squared plus 6x plus 9 is x plus 3 all squared. Remember to distribute 1/3 times negative 9. So 1/3 times negative 9 is minus 3 minus 4. So overall, we have 1/3, y equals 1/3 times x plus 3 all squared minus 7. This is the vertex form. And if I go back and compare, it is exactly what we got the first time.